Hello everyone, this is Dilip. In the last video, we have seen about machine learning. We have seen various definitions and we have seen various types of machine learning, supervised and unsupervised. In the current video, in the coming set of videos, let's look at supervised learning in a much more detailed manner. Let's start with linear regression with one variable. So here we have a set of data marked with X, where the size of the house will determine the price of the house. So just like in the last video, let's ignore other parameters like location of the house, etc. And we have a set of 11 data points. So this will be our training data, which we will feed into our learning program, which will determine a linear hypothesis which will fit this data. Okay. So this will be our flow where we feed the training data into our supervised learning program, and this will result in a hypothesis. A hypothesis in the current scenario is nothing but a linear regression. So here you can assume, since we are dealing with linear regression, the hypothesis will always be a straight line. When we deal with much more complex programs, the hypothesis can be a non-linear picture, like exponential function or something similar. Okay, so here it's a straight line since, okay. And once we give the high size of the house, it should determine the price of the house. And the reason it's called linear regression is called because we are fitting a straight line to this. So it's called a linear, and regression because it's a continuous valued output. And if we try to fit a straight line into it, so let's just try some straight lines. So if you put a straight line like this, it doesn't fit our data. And if you put a straight line like this, it doesn't fit our data. If you put a straight line like this, it doesn't fit our data. But if you fit a straight line like this, sorry, this doesn't look like straight lines, but assume these are straight lines. This almost neatly fits our data. And any straight line, you know, it has a following equation: theta 0 plus theta 1x, where theta 0 and theta 1 are the parameters which will determine whether a straight line will be like this, or like this. Okay. And expected output is y. So for our given training data, say wherever you see this x marks, this is our training data. We know the value of x and the value of y as well. So we know the expected output. And if we draw a straight line like this, which is our hypothesis, and we calculate the h of x, which will be the calculated output, and the calculated output minus real output will give us how much our hypothesis function is deviating from the original result. So if you measure these distances, this distance, this distance, this distance, this distance, so how much our hypothesis is deviating from the actual result, sorry, expected result. So this should give us the difference, and as much as we minimize this difference for all the training data, that will help us in minimizing our loss. So I'm calling a term here loss function, which is nothing but for a given single training data, the deviation from the calculated value to the expected value, this will call a loss for the training data. And if we measure the loss for all the training data together, that is called a cost function. So our goal is to minimize the cost function such that the deviation, it will automatically result in the reduction of deviation and will help us in getting a better hypothesis. Okay, let's move on to the next slide. Okay, so here the hypothesis is theta 0 plus theta 1x because we want to fit a straight line into our data. The parameters are theta 0 and theta 1. The cost function is nothing but, so here I, you can assume it to be ith training data, and h of xi represents the calculated output for a given input training data of xi, and yi is the expected output. So the deviation we are calculating and we are squaring it. And for all the training data, so this m represents the number of training samples. So for all the training data, we are summing up the square error. So since this is called error because this is what is deviation. So the square error, and we are calculating the average. So this 1 divided by n, and we are multiplying with 1 by 2. It's a constant, so its value doesn't change much. So the square error we are calculating, and then we are doing a division with the total number of training samples. So this is called mean square error. So if you see a term called mean square error, it's nothing but our cost function, which is here calculating the deviation of the training data. And our goal is to minimize the cost function for a given theta 0 and theta 1. And we have to keep changing the values so that we can minimize j of theta 0, theta 1 cost function. And after minimizing this function, and if we come to know that we cannot minimize it further, then we can fit these parameters to our training data, which will give us our hypothesis. So to explain this better, let's take a simple example. So this should be y here actually, but maybe mistake it this h of x. Okay. So given a training data like this, so we have only 3 data points here, where the value of x is equal to the value of y. Okay, you can see the value of x is equal to the value of y. Same here, the value of x is equal to the value of y. Now, given this data, so here I'll give you the answer straight away. Here theta 0 is 0 and theta 1 is 1. As you know, so our hypothesis will become h of x equal to just x, because theta 1 is 1 and theta 0 is 0. And you can see our h of x will be a nice straight line like this. And it fits all the data points. So here I'm not able to draw it properly, but all the data points will fall into this. Once you have the hypothesis function as h of x equal to x. Now, what will be the cost function for this? So as you vary theta 0 and theta 1, and you know, like when theta 0 is 0 and theta 1 is 1, we got the correct hypothesis. And when theta 0, with theta 0 we are not representing here, but theta 1, when theta 1 is 1, we got a correct hypothesis. So here this is a cost function being plotted for different values of theta 1. And when theta 0 is made constant, like when theta 0 is just made 0, and you keep changing the theta 1 values, you can see the cost function getting deviated. And you will get the minimum cost function only when theta 1 is equal to 1. So this helped us. So I am actually went from hypothesis to cost function, but the correct way is calculate this cost function such that where the cost function will be minimum, that parameter you will fit into our hypothesis. And this is because here we made theta 0 as 0 for a single parameter, the cost function will look like a parabola. Say both theta 0 and theta 1 are varying. So in that case, our hypothesis function we have to represent in a three-dimensional way, where the height of this plot we have to minimize such that you can see there will be a bottom for this that will determine the lowest value for the j of theta 0, theta 1, which is the cost function. And what are the parameters theta 0, theta 1 are present there, those will give us the minimum cost function, and those we can fit into our hypothesis function. And this is one more example of a hypothesis function. And this 3D plot, you can make it 2D, and if you just look at it from top or bottom and just draw circles like this, these are called contours, and if you just draw circles around this will result in a cost function looking like this. So the 3D function we have put it in a 2D manner. So this is called contour. We'll discuss more about this in the later slides. And here you can see an example of hypothesis function where given a training data, we have fitted hypothesis, and you can see this hypothesis almost fits nicely to this training data. And there will be some other hypothesis. Say for example, there will be hypothesis like this, there will be hypothesis like this. So if we keep changing theta 0 and theta, there will be different hypotheses like this. And we start with some hypothesis here, and we slowly move on to the center. So sorry, we start with just the theta 0, theta 1 parameters, and by modifying theta 0, theta 1, our goal is to slowly move to the center of this such that the cost function will be minimized. At the same time, you will see you will be getting a line similar to this blue line once you reach the center of this. So in short, once you minimize the cost function, you will automatically get a very good hypothesis. So how do we move from how do we move like this? So here, since we are manually moving it to the center, we know because selecting theta 0, theta 1 values, we can manually move. And in the next set of videos, we will see how to do it in a programmatic manner. Thanks for watching the video. So if you have any questions, please leave in the comment section. I will try my best to answer them. So let's look at how to optimize the cost function in the programmatic manner in the coming set of videos. Thank you, everyone.